Good morning, welcome. Appreciate everyone attending the first mass conference here in the U.S. I'd like to thank you for that attendance and also extend my thanks to Craig Rollins and his teams. My name is Casey Malmquist. I'm the president of SmartLam. We are the first CLT manufacturer in the U.S. located in the Flathead Valley, Montana. We started our operation in 2012 and have enjoyed 4 crazy years of fun and excitement in this exciting new industry. So today I'm going to talk on a part of the APA PRG 320 requirements and specifically quality assurance, which can sound somewhat mundane, but we're actually right in the middle of this process, and it's actually been very interesting and quite exciting. So because that might be a little mundane, I'm going to give you a little eye candy. I've got a couple of film clips here of some recent projects we've done. They pale in comparison to some of the stuff you saw earlier today, but you know, we are a grassroots effort here in the U.S. right now, and you eat elephant one bite at a time, and we've got lots of little things going on, and we're just looking at it. We too have lofty ambitions to be involved in these tall wood buildings, but in the meantime, and I think a more realistic entrance into the market is going to be at the grassroots level, smaller projects and components in buildings rather than the entire white elephant. So we had a little bit of a technical problem, so I need this gentleman here to get this first video going. So this next slide is an animation of a product. I spoke earlier about getting some components into projects. We have a number of areas that we're working on, including CLT elevator shafts. And we've kind of created a little animation here comparing it to the conventional method using concrete masonry units. And it's pretty compelling. And this is one of several things we're developing for modular staircase enclosures, elevators, deck systems on typical multi-story, multi-unit buildings that are already in existence. But this gives you a very good idea of the comparison with the speed of build and the complexity of a build. In this case, you have several inspections that need to occur. It's very weather dependent. It's got a large group of people working on it. Lots of logistics. We feel this is a much cleaner and better way to create the same structure. This is an actual elevator shaft we modeled there in the animation, but this was sold to a company in Quebec and went into a retrofit building. And these are the pictures after the installation. So these are a start. So I recently had a discussion with an associate of mine who was frustrated with us. We announced last year that we had all intentions of building a new CLT plant and have it up and running this year. And I was explaining to him that, in doing this in 4 years, the more we learn what we don't know. And I'm actually grateful we've waited, because I think the plant we would have been built then, we'd probably be doing modifications on it now. And his response was, what's the big deal? You're just bleeping gluing 2x together.
I think the tricky confusion comes around wood when you're looking at carbon and composite wood, because there are different reporting methods of
What could possibly go wrong? One of the things we've learned, it's a very intricate process. And an associate of mine also compared it to baking bread. Making CLT is like baking bread. A baker is a much different job than a chef. A chef can get creative, throw in lots of crazy ingredients, tamper with this, mix a little of that, throw something else in here, and you can come up with something really delicious. When you're making bread, it's a very formulatic process, and you miss one step, if you screw up anything, it's not going to work. I mean, the correct ingredients, proper sequence, the suitable environment, and you get perfect bread. In our experience, you have to replicate these same elements to get perfect CLT. So today, the quality assurance part. What is quality assurance and why does it matter? And where does it fit in with the APA 320? Quality assurance really is kind of the last part of the process. With the APA, the very simplified version of this, they visit your plant, they do a plant pre-qual, they look at your machinery, they look at your process, they look at your people, you have to build a lab, they look at your testing equipment, they take some of your product, they do some on-site testing in your lab to make sure that what you're doing and how you're doing fits within the APA PRG 320 regulations. From there, you take, that product is then sent to the AP lab in Tacoma, where they do some structural testing, which includes stress and bending and the shear tests. But the daily bread really falls on the shoulders of the manufacturer, and that's in the quality assurance measures. And that's where the real work comes in. So what does this take? This is a photo of the lab we built smack in the middle of our plant. Of course, it's made out of CLT. This is the floor pan for that, and then kind of the essential ingredients, which is a lot of cool tools. I mean, moisture meters, humidifiers, adhesives testing, microscopes, the whole lab furniture. My favorite was I got a lab coat and a pencil protector, pocket protector, which was pretty cool. Inside shots of our lab. So some of the key pieces of equipment in that lab, this is a shear block tester. So this is where we cut up chunks of sample CLT, and they're put in this press and that very fancy shear block device on the left, which, believe it or not, looks very simple. Apparently there aren't a whole lot of them around, and we had to make that one, and it cost over $5,000 to make that little device. So you outfit the lab with a bunch of fancy looking equipment that looks expensive and costs even more. Here is the cyclic DLAM test equipment. You've got an oven, you've got a pressure cooker. And actually, I think you probably could make bread in that lab if you wanted to. This particular piece of equipment, this is a finger joint tester, and the board is grasped on both ends by hydraulic rams, and then they literally pull that board apart. The idea is for the board to fail rather than the finger joint. And this is, again, part of the ongoing process. So the tests that go on a regular basis in that lab, in fact, we have to test at least once per shift on those samples. And if we run in excess of 50,000 board feet, we've got to test at that metric as well. And we're testing the finger joints again for tension test, and then the cyclic delamination. And the cyclic delamination is basically boiling that piece of wood for a period of time, putting it in the oven, drying it out, putting it back in, boiling it under pressure, and doing that several cycles. And it emulates like a 10-year exposure for that wood element. And what you're looking for is to make sure that that face bond or finger joint does not delaminate. On the face joints, again, it's with the block shear testing and the cyclic delam testing that face bond as well with that protracted exposure. So in the PRG 320, this is the chapter on quality assurance. And there's a lot of technical jargon in that document, and it's all very valuable. But best summarized are the objectives that were provided by the APA. And those objectives simply are exercise assures every machine, every process, every element, and every person is doing the right thing in the right way in the right time. So again, there's two basic forms of testing, what we call inline testing and offline testing. And this chart kind of describes those two methodologies. Inline testing is conducted on the actual CLT manufacturing line on a daily basis. There's essentially 13 processes that occur while manufacturing CLT. In these processes, there are several pieces of equipment. The infeed, finger jointing, planing, stacking, the adhesive application, pressing, and CNC and finishing. Offline testing. Offline testing is the testing that goes on in the lab that we just talked about, finger joints and the face joints. These samples are cut out of, just randomly cut out of sample or a product that we are producing. The APA gives you a chart as to where to take these samples. We then record that data, and they inspect those recordings on a regular basis. And if there's any sort of deviations or aberrations, then we're required to send them back into their lab for retesting. A little deeper on the daily QC inline. It's everything from moisture control, so the inbound material. We have a scanner at the front of the line that tests for moisture content, a very essential part of the recipe in making CLT. Wood surface quality. In order to get the 80% face bond and fiber tear they're looking for in these metrics, you have to make sure you have a good, flat, undisturbed face, which will include lack of knots, lack of planar chatter, wane, all of the defects that might affect that face contact. Temperature is a real key issue. The adhesives are temperature sensitive. During the course of the year, our wood product could come in, from 20 below to 90 above. So moderating and controlling that temperature is part of the process. And of course, the finger joint quality. And any of you who are familiar with finger joints know there's a lot that can go wrong there. More on the inline. Adhesive spread rates. It's very important to apply a specific amounts at a specific rate to get the continuous coverage. Assembly duration. All adhesives have an open time, and so these panels have to be made up within very specific time limits. And then the press duration. The loaf of bread has to be cooked for the proper amount of time. So the final one is just the, So again, this is the daily offline charting here, which includes all the stuff from the lab. And then finally, we have this finished product inspection. So once that element has come out of the entire process, including post-panel fabrication and finishing, it's inspected to meet the requirements, again, that are listed in the PRG 320 quality assurance. And those are the kind of things we look for: the width and depth, length, straightness, squareness of that panel, dimensional stability, confirming the species and the grade, number and orientation of the plies within that element, the industrial architectural finishes, whatever finishes have been specified, and then again, a measure of the finished product's moisture content as it goes out into the field. So that is a brief introduction to the quality assurance program. Thank you.